Hello everybody. Now we are going to discuss the third case. Let me just go to this slide so we know where we are right now. So we already discussed the type 1 problems for the turbulent flow where we calculate the losses or delta P. And then the second type where we calculate the velocity or volumetric flow rate or mass flow rate. And this is what we discussed last time. And now we're going to see how to deal with the last case where we are interested in calculating the diameter of the pipe. So this is the third case, and it would be the one that's most it's not most difficult, but I mean it includes more steps, just one more step or two more steps than the previous case. But it's going to be also solved iteratively, and we will see why we are going to do this. So this problem that we are going to discuss here is about a pipe that is used to transport water, air, at 1 atmosphere and 35 degrees Celsius along a 150 meters pipe at a rate of 35 meter cube per second, and the head loss is the allowable head loss is 20 meters. So this is the maximum head loss that that's allowed. Okay, and we need to find the diameter, and we know the viscosity of air. So before we go through any details, there are some information that we have to know before we do anything. The first is the properties of the fluid. So the fluid, we know the viscosity, but we don't know the density. But it's air at 1 atmosphere, so we can consider it as an ideal gas. So from the ideal gas law, we can calculate the density, which is 1.14 or 115 kilograms per meter cube. The next is that there are parameters that are used a lot in more than one term in the equations that we use. One of them is the velocity. So velocity is, we don't know the velocity, but we know the volumetric flow rate. So the velocity is the volumetric flow rate divided by area, but the area is pi over 4d squared, so we don't know the diameter. So here is the first time we will see the diameter, that the velocity is the volumetric flow rate divided by diameter power 2. And the velocity is needed to calculate the Reynolds number. So by substituting a Reynolds number, we will find that Reynolds number is 27,000, almost 27,000 over d. So it's constant over d squared multiplied by d. So it's going to be all divided by d. And from this we can confidently know that it's going to be turbulent flow. And the reason is the diameter will never reach, or it's not will never. The common case is that it's in the range of centimeters, 10, 20 centimeter maximum. So when we have a diameter of let's say 1 meter, for example, then this would be 27,000. So it's turbulent. So in the normal range of diameters, this would be around 200,000 or something around this. The next is the epsilon over d. So we don't know epsilon, but we know that it's plastic duct, and from the chart we will find that plastic has roughness of 0. So this is good news because it will simplify the calculation somehow. So when we calculate epsilon over d, it's 0. So we can, if we use Colebrook equation, then epsilon over d would be cancelled out, and we will have this equation, this term only left inside the log, and this is the equation we use for the friction factor. Now we have equations for everything except for the losses, so we can write the formula for the losses, and we know that H loss is FL over D times U square over 2G. And now this is a very important equation, and I want to focus here more on this the last equation that we have. So you see here that H losses is inversely proportional to the diameter power 5. And this is very important. This is very important point. So in the beginning of this chapter, when we were discussing the pressure drop in laminar flow, when we derived the Poiseuille equation, we reached the conclusion that delta P is inversely proportional to diameter power 4. Okay, it was diameter power 4, which means that the as we said, if the pressure drop is, let's say, 1 atmosphere and the diameter is reduced to half, then the pressure will be 2 power 4, so it's 16 times. So it's from 1 to 16. This is in laminar flow. But in case of turbulent flow, it's going to be d power 5, which means that if we have the same case, the same diameter and the same losses, and the diameter is reduced to half, it's not just only increasing one number in the power. This number in the power means that the loss in laminar flow that is going to turn from 1 to 16, in turbulent flow it's going to be from 1 to 32. So it's double the loss in case of laminar flow, and this is a lot. Having this pressure drop increased from 16 to 32 is a lot, and it can mean a lot of money that we need to pay for pumping and for and this is something we will discuss later about the choice of the diameter. But the point I want to make here is that we mentioned before the pressure drop is very sensitive to the diameter in case of laminar flow, and it's much more sensitive in case of turbulent flow. So again, increasing the power by 1 is not a small thing. It's a big deal. It's a very big deal. And this is why there is one very famous engineering problem, which is the optimum pipe diameter. And maybe this is something I will discuss later, that how the diameter affects the cost of the pipe and the cost of the pump that's being used, and it's something that is very important. So anyway, so this is something we will discuss later. So for now, this is the equation that we have for the losses, and now we can rearrange the equation to be diameter as a function of friction factor, and now we will reach the same point that we reached before. We have three variables: friction factor, the diameter, and Reynolds, and and Reynolds number. And we want to calculate the diameter, but the diameter is needed to calculate Reynolds number, which is needed to calculate the friction factor, which is needed to recalculate the diameter. So still we have the same endless loop. So in order to find a way to calculate the diameter, we have to solve these equations by trial and error. Keep in mind that these are three equations and three unknowns, so there must be a solution to these three equations. But the solution needs trial and error. So let's again, we also last time we mentioned that we have the freedom to assume whatever we want to assume from these parameters. You can assume the friction factor, you can assume the diameter, or you can assume Reynolds number. But we said that friction factor is or it's more recommended because the range is narrow and it's easier to assume a value. No matter how far is it's going to be close to the correct answer compared to the Reynolds number and the velocity. So here I assumed a friction factor. I don't know why I picked this number, but I just picked it as 0.0002. And from this we can substitute in the first equation to calculate the diameter, which is 0.109 meters, and then from the diameter we can calculate Reynolds number, which, as you see, it's almost 250,000. And we know epsilon over d is 0, so from the friction factor we can calculate it. So let's again, I like to do this every time just to confirm that what we get from the chart is the same what we get from the, or close to what we get from the equation. So we have here the chart for smooth pipe, and if we check the previous the chart that we have here, it has this line. It says smooth pipe and epsilon over d is 0. So it's the same thing, but I prefer to go for the second chart because this table will make it difficult to find the correct spot. So anyway, so here we have 2.5 times 10 power 5, so this is 10 power 5, 2 times 10 power 5, this is 3 times 10 power 5. So 2 times 10 power 5 is this grid line, and now we are going to intersect this line with the smooth pipeline here, and then we can oops, I'm sorry, so this is the line that we have, and this will be 0.015. Okay, so this is the friction factor that we we should get from the equation. So the equation gives 0.0149, which is very close, which is very, very close. 0.0149, and it's clear that this is almost 75 times the friction factor that we assumed, so it's not equal. So we'll take this as the new assumed value, and then we'll recalculate the diameter and then recalculate Reynolds number. Let's go back to the chart and see it's I'm sorry, it's 105,000, almost 100,000. I'd say it's almost 100,000. And then let's go to the chart. The 100,000, it's 10 power 5. If we see here, this is going to be 0.01. This is 567, 0.017. Okay, so this is 0.017. So let's go and check what we get from the equation. It's 0.0178. So it's close. It's very close. And we can keep going, and this is what we get after 5 trials. So for the first trial, it was 0.0002, and then it became 0.0149, and then 0.0149 to 0.0178, from 0.0178 to 0.0179. So it's getting very close now, and from 0.01794 to 0.01795. So finally, we can reach this point where we have the velocity is 0.267, and the velocity is calculated to be 6.25 meters per second, and the friction factor and Reynolds number are already calculated. So the procedure for the trial and error is the same. It's just writing the equations in the right way. And I think this is one of the very, very important parts, is to know how to write the equations properly, so that you can do this iterations well. We can do what also we did last time, and I prefer this case or this procedure if you have the chart, because with the chart you can or you have to go through the equations one by one. But also you can use the second approach, which is combining all the equations together in one equation. So here we have, this is the velocity, and this is Reynolds number, which is 27,000 over the velocity. So if you want to do this kind of manually, so you assume a value and then recalculate it, and then take it as a new assumption, recalculate it, this is what you're going to get, the same output as the previous case. So this is the third type of problems. Inshallah, next time I'm going to do what I did last time. So I'll show you how to do this using Excel, and then we will see. I haven't decided if I'm going to do this optimal pipe diameter now or keep it for later. But for I definitely have it on the list of things to present here. I don't have it as part of the course slide, so that's why I'm not sure if I'm going to go for it now, or we'll continue the course and then we'll do this later. Anyway, so I'll inshallah I'll do this. So I'll see you next time, inshallah. Goodbye.